Yeah, okay, much better for now.
Okay, so let's, well,
Okay,
did anyone have any ideas?
yeah, I was just repeating the problem statement. So do you guys have any ideas?
Yeah, the prism idea, you split the spectrum and then maybe via fiber optics or something assign each spectrum its own portion of the cell.
Yeah, that's great. Yeah, that makes sense. So I don't know if everybody kind of appreciated that. The idea was to use a prism to separate the wavelengths out, and then use different materials to absorb it. Yeah. There might be are there any other?
How do you account for the total area? Because that if you split light with the prism, you need to increase the area of the panel.
Yeah, that's a very good question. So you might also want to do concentration. So very good point. So the solution that we worked on.
Important points. So if you combine them, you can get the solution. Anyway, sorry.
Yeah. So I'm going to talk about the solution that we developed, which is along the lines of both your solutions that you pointed out. So we decided to create an optical element which will take sunlight and separate the colors. Okay, in this example, we're only showing two different colors. It's kind of like a prism, but it's flat as opposed to a prism being fairly bulky, because it works by what's called diffraction, and we call it a polychromat. So in this example, what it does, it takes the sunlight and puts the red portion of sunlight, which is just a cartoon, of course, just a schematic, on the left-hand side, the blue portion of the sunlight on the right-hand side, and then we put two different solar cells to absorb them more efficiently. So the idea is that one solar cell has some material which can absorb these photons very efficiently because they're close to the band gap. And on the right hand side, you have another another solar cell that can absorb these photons very efficiently. Now you can see two things have happened. This optical element has separated the colors, but it also has concentrated the light. It has taken the incident light and concentrated it onto the solar cell. So it has addressed the two problems that you pointed out. So, and of course, the idea is that you can make this in a huge periodic array. So you can, this is one unit, periodic unit, and you can use an array of these. So imagine the whole thing repeated in infinity to the left and right. Okay, so the idea is conceptually simple, but it's a little bit complicated to actually do. So the device itself looks something like this, and it's designed using fairly sophisticated algorithms, but it has some fairly complex structure, as you can see here, and it's at the micrometer scale, so it's fairly thin. And if you zoom into this area, you can see the structure, which looks like that. Okay, so it's about 10 microns in width and about 1.4 microns in depth. And the idea is that when light is incident on this kind of acts like a diffraction grating, but a very special diffraction grating that takes the blue portion of the light, which is this part of the light, 400 to about 800 nanometers, and puts it on the left-hand side of the image. And it takes the red portion of the light, which is 800 to 1000 nanometers, and puts it on the right-hand side of the image. So this is a plot. So the image is, of course, one-dimensional. So this plot is a 2D plot, which shows this dimension is the direction of the position of the image, which means that you're scanning along the image plane in this direction. And this is the wavelength. So you can see all the high energy bluer photons are here, and the lower energy red photons are here. So I can put a high bandgap material here and absorb this very efficiently, put a low bandgap material here and absorb this very efficiently. Of course, it's a little bit of crosstalk, which you can see here as well, so it's not perfect. And you can plot what's called optical efficiency as a function of wavelength, where you define the efficiency as, what is the probability that light ends up in the right location. So, for the blue plot, the probability, what is the probability that the photon will be on the left-hand side? And for the green plot, what is the probability that the photon will be on the right-hand side? And you can see the probability is higher for the lower wavelengths or higher energies. And here, probability is higher for the redder wavelengths and the lower energies. And the average efficiency you can extract from both of these about 74%. So it's not 100%, of course. So it's not perfect. Oops. Okay, so then the idea, again, to remind ourselves, the idea is to use the device here. Sunlight comes in, and the red portion, the lower energy photons go over here, high energy photons go over here. Okay, and this is what the device looks like. There are a bunch of grooves. Okay, and if you look at a dark field image, you can see the edges of the grooves. It's about 10 microns. In a profiler image, you can see the structure in a little more detail, and you can see there are multiple height levels as well. We use a technique called grayscale lithography to pattern this. The idea is fairly simple. You have photoresist on top of glass, and by simply changing the dose of light, which is using a laser, UV laser, onto the photoresist, and by controlling the energy that you put down, you can control after development how deep the photoresist is removed. So higher the energy, the more the photoresist is removed. Lower the energy, less of the photoresist is removed. And by very carefully controlling this, we can create these multi-level structures as shown here. So you can kind of see, so you put more energy here, less energy here, and so on and so forth. But the eventual vision is to be able to do this at, in high volumes by using embossing. So this would be like you have a pattern which is on a cylindrical drum as shown here, and as the film passes through between this drum, it embosses the pattern onto it. After it, of course, it's heated before in order to soften the polymer, and then it cools, and then it gets replicated and laminated onto a substrate. So you end up with this large parquet of these polychromats. That's the idea. For optical characterization, it's important to understand that, again, this is kind of tying to the lecture from last lecture, where we talked about how important it is to do the optical characterization carefully. So in this case, we had to build our own solar simulator. And the example, we took a lamp, which you can see here, fairly big, bright lamp with a fan because it has a lot of power, it's very hot. And then we have a pinhole and a lens to try to expand the lamp and make it nice and collimated. So then we let the beam propagate over a very long distance from here to here to here to here. It's a little more than 2 meters. So, and the idea is to essentially emulate or simulate what happens to sunlight as it passes from the sun all the way to the solar cell on Earth. So it's a very long distance. Of course, this is very much older, but it just simulates the effect. Then we have the polychromat placed here, which is difficult to see because it's transparent on glass, and then the solar cells right there. So it's an example. So in order to, before we actually measure the solar cells, we have to actually see what the polychromat itself does. So you can see the devices here, and there are 3 periods of them. So as I said before, the grooves can be periodic, so they're repeated. And you can see an image here at some distance away. And the period is 10 millimeters, so 1 centimeter. And you can see these dark band, which is the infrared band, which is the lower energy photons. And this bright band is the visible band, which has the higher energy photons. So the idea would be to put a low band gap cell here and a high band gap cell here. Okay. And we can actually measure the performance of the device with a spectrometer. So you put a fiber input to a spectrometer in the image plane. So there is the device. It's illuminated with white light. It creates this spectrum split image here. And then we put a spectrometer here, which is a fiber, and move it on a stage. So it's a scanning stage that we can manually move. As you move the stage, you can measure the spectrum. Okay, so you can see how much energy is per photon. And we also have a track to set the distance between the polychromat and the spectrometer. And the output of this looks like that. on the right-hand side. This is what we measure. So the spectrometer measures a line through this plot, okay? A vertical line here, which is in wavelengths, goes from 400 to 1,000. So that's the measure of the spectrometer. And then we step over and do another measurement, and we step over and do another measurement, and so on and so forth. So this is the position of the spectrometer, and this is the output of the spectrometer. So the vertical axis is wavelength, the horizontal axis is position. Here you can very clearly see that the short photons are on the left-hand side. So the short wavelength photons are on the left-hand side, the long wavelength photons are on the right-hand side. The high energy photons are here, low energy photons are here, and it agrees more or less with the simulation. So this is the simulation, that's the experiment. Okay, now we know that the optical device more or less works. We can start putting the solar cells down and start doing electrical measurements. Before that, of course, we can also calculate the optical efficiency. Just like before, this is a simulated optical efficiency, this is a measured optical efficiency, and they're pretty close. Not perfect, but pretty close. Now we can put the solar cells and do electrical measurements, and this is what it looks like. So in this example, we used two different materials, gallium indium phosphide and gallium arsenide. And we can look at the performance of the materials by looking at the external quantum efficiency. So here, the gallium arsenide has external quantum efficiency shown by this red curve, which means that it absorbs a much larger band because of the smaller band gap. And the gallium indium phosphide has this blue curve, which absorbs a much smaller band because of the higher band gap. Okay, so again, the wavelength goes from 350 to about 900. And if you do the reference electrical measurements, simply take the cell and illuminate with white light and simply measure the spectra, you see something like this. Okay, so that's voltage, and of course current is negative because it's reverse bias, as we know. And the light conditions are pretty low light because remember our lamp is placed very far away from the cell. So remember the light is basically expanded. And gallium arsenide has a curve like this. And one key difference here and here is that if you look at the open circuit voltage, which is here, and the current is 0, for gallium arsenide it's about 0.85 or so, and for gallium indium phosphide it's a little bit higher, closer to 1. Okay, so you can see this has a higher band gap than that. That's why the open circuit voltage is higher. Now the short circuit current is a little bit higher for gallium arsenide because you have more photons, right? From this plot, we know that this collects more photons and hence produces more current than this. So the short circuit current density is actually higher for gallium arsenide than gallium indium phosphide, and this is expected. And then we had a slightly different polychromat, not terribly important for us, but it looks very similar to what we've seen before. The short wavelength light is on the left-hand side, long wavelength light is on the right-hand side. It has a slightly higher efficiency, so it's a little bit different device. And this is what we expect to see. We can simulate what we expect to see in experiments. So these are electrical measurements. Again, the voltage is biased. Current is measured. This is simulation. This is the reference value, which we just saw, curve. And this is what we expect to see with an ideal polychromat after spectrum splitting. So you can see the curve has jumped up. The current has increased quite a bit, right? Almost 50%. And open circuit voltage has increased a little bit. And that is primarily to do with the concentration. And for the gallium arsenide, the decrease is much less, primarily because you're already absorbing most of the light. This is more dramatic because it's not absorbing all that extra light very efficiently. Remember, let me explain what I mean. Remember, the gallium indium phosphide cuts off around here, right? Beyond these photons are not absorbed. So this is completely wasted. And with the polychromat, these photons, which are not absorbed by gallium indium phosphide, is redirected to gallium arsenide. Okay, so it's not wasted. So yeah, so Now you can of course plot the simulated power voltage curves, which is power is simply current, and in this case it's power density, which is current density times voltage. This is in milliwatts per centimeter squared as a function of voltage. Again, you see the reference curve, and we know there is an optimum value as we saw in the last lecture. So that's the expected reference curve. This is the simulated curve with ideal polychromat, and you can see clearly the maximum power has jumped up quite a lot. Again, 50% here. But for gallium arsenide, it's much less increase, but still there is an increase. If you average them both, the total power predicted to increase by about 28%. What do we see in experiments? So that's the device we made. Again, we can measure the optical performance. The high energy photons on the left-hand side, low energy photons on the right-hand side. We measured this in exactly the same way as we explained before. The optical efficiency is plotted here, that's simulated, that's measured, and they have pretty good agreement. Now is the fun part where we do the experiment. Here you can see the polychromat, which is kind of like the prism. And here you see the different solar cells. So that's a gallium arsenide solar cell, and that's a gallium indium phosphide cell. These are commercially available. You can buy them, but in our case, we obtained these from the National Renewable Energy Labs because we were doing a collaborative research project with them. So the idea is to essentially put this at the right location of the spectrum, measure its performance, electrical performance, and then move over and put this in the right part of the spectrum and measure its electrical performance. And this is what we get. So gallium indium phosphide, this is the reference. Reference is with without the polychromat, so just the white light. And this is with the polychromat after the spectrum splitting and concentration. Clearly, there's a nice improvement. Not as much as we expected in the simulation, but nevertheless, it's quite large. Okay, increase in current, also increase in open circuit voltage. In gallium arsenide, you also see a pretty nice improvement in current, slightly better than what we expected actually. In this example, also increase in open circuit voltage. And we can plot the same data as power. So this is power density versus voltage, and that's the reference measurement. And this is with the polychromat. Again, you see a pretty nice increase. And same thing for gallium arsenide. If you average them, we measure an output increase of about 16%, which is quite a significant number, considering all we're doing is simply optically separating the light and concentrating it. We're not changing the solar cells themselves. We had some discrepancy between the experiments and simulations, and we can address these discrepancies by looking at the measured optical spectrum. I won't go into the details, but essentially the discrepancies come from the fact that the polychromat itself is not ideal. You end up losing relatively about 10-15% of the light from the theoretical predictions. So I'll skip that part. Actually, let me just to summarize. So what we end up seeing is this: that we measured an increase in our power of 16%, the predicted increase in our power of 28%, and we estimated an increase in power with the loss of the polychromat about 22%. We're still off by about 6%, but it's relatively close. Of course, all of this is great, but the next question is, what sort of efficiency is actually possible, right? So this has been studied in great detail by this very interesting paper from actually Lucent Labs, AT&T Lucent Labs back in the 1980s. Which plot and this guy Henry here plotted the energy, the bandgap energy, as a function of the number of photons that can be accumulated from the sun, and you get a plot like this. As the bandgap energy decreases, you're collecting more and more of the photons, and the area under this curve represents the efficiency. Another way to look at it is basically shown here. Let's imagine you have a concentration factor of 1,000. If you have a single band gap, the maximum efficiency you can hope to achieve is 37%. If you have two band gaps, you can get 50%. If you have three band gaps, you can get 56%. If you have 36 band gaps, you can get 72%, and so on and so forth. So the idea here is that by going to more and more band gaps, you can increase the amount of photons that you're collecting more efficiently, and as a result, increase the whole system level efficiency as well. And this is just a simple example that we can actually design polychromat for many, many spectral bands. So this is an example of 4 spectral bands where we're separating the colors out in 4 bands. This is just a simulation, but you can get the idea. So you can go to very, very high precision. So in the future, imagine theoretically, if you are able to essentially tailor every photon to its own material, then you can get close to the thermodynamic limits of over 50% or so. I think the holy grail for a lot of solar cell designers is something like 50%. That's kind of like the next big goal. So with that, I'm going to stop this and talk a little bit about next week's lecture. So let me first ask if there are any questions before I do that. So for this lecture, what I recommend, of course, is take a look at the notes, make sure you understand the basic concept. They're relatively simple, and just be aware of technologies that exist to improve the performance of photovoltaics. Okay, so next week we're going to shift gears a little bit, and I want to talk a little bit about what you need to do before you come to class on Tuesday. So first of all, like I said, we are going to do something called a business model canvas in class. And in order to actually do this, I need you to watch these lectures on Audacity first. So the link is here, so you can click on it. I've already signed up, so it goes on to my account. So, but it's a free account, you can get started. So actually, let me sign in. And I'll just walk you very quickly through it. You can sign in. I signed in, and there's a class called How to Build a Startup. So it's already in my account, so I can see it here, but you can go in and search for it in the catalog and you'll see it. Okay, and so just sign up for it. And you can go to the class, and the lectures are all listed here. So I would recommend going through lesson 1, lesson 2. So these are just introductions. Lesson 3, which is the business models and customer development. Lesson 4, business models, so they're related. Lesson 5 is the value proposition. Lesson 6, customer segments. Lesson 7, channels. 8, customer relationships. 9, revenue model. 10 is partners. 11, resources,